Hello, welcome to part 5 of the chapter 6 lecture video. In this particular part of the video, we will be talking about thermochemical equations. Those are equations with delta H embedded in them. And we'll talk about Hess's Law, which is a useful relationship showing that thermochemical equations can be added together, give the overall value of a chemical equation. First, we're going to talk about some thermochemical equation rules. A thermochemical equation is just a chemical equation plus the value of delta H. For this particular reaction, methane, CH4, can react with oxygen to make CO2 and water. 800 kilojoules of energy is released. Delta H is negative 802 kilojoules. The delta H value for the reaction is per mole of substance in the chemical equation in terms of the coefficients. So the coefficient of methane is assumed to be 1, oxygen is 2, CO2 is 1, and water is 2. We can develop some ratios to show these useful relationships between the delta H and the number of moles of the reactants and products. So for methane, CH4, there's 802 kilojoules per 1 mole of CH4. For oxygen, it's 802 kilojoules for every 2 moles of O2, where the 2 in that ratio comes from the coefficient. CO2 is back down to 1 mole, and water, H2O, also has 2 moles of H2O in the denominator. Here's an example that will show you how this relationship between delta H and number of moles of substances can be useful. Here's a thermochemical equation of sulfur dioxide reacting with oxygen to make sulfur trioxide. The delta H is negative 192.8 kilojoules. We can use those relationships of delta H per mole to calculate the delta H of a reaction, or how much heat energy is released, for a reaction that produces 200 grams of sulfur trioxide. First, we can start by taking the mass of the sulfur trioxide and converting it to moles. Once we know the number of moles of sulfur trioxide, we can use that ratio of 192.8 kilojoules for every 2 moles of sulfur trioxide. This works out to be 482 kilojoules of energy, and this is the amount of energy that is released to the surroundings. We know it's energy released because of the negative delta H. In thermochemical equations, fractions are okay, and in some cases, fractions are necessary. Delta H, of course, is proportional to whatever the fractions are in the chemical equation. We can look at the first equation. If 2H2 plus O2 makes 2H2O, we have 1 delta H of negative 484 kilojoules. If we divide each of those coefficients by 2 to give 1 H2 plus a half of an O2 goes to H2O, the delta H is 1/2 of that value, so it works out to be 242 kilojoules. If an equation is reversed, the sign of delta H is changed. So for the above equation, H2 plus half O2 goes to H2O. If that equation is reversed, so H2O is turning into H2 and a half of an O2, the delta H becomes positive 242 kilojoules. What this really means is that in one direction, energy is released, and in the opposite direction, energy must be absorbed. In thermochemical equations, the states of matter matter. H2O gas plus H2O liquid has a delta H of negative 44 kilojoules. If we don't have the proper state of matter in the chemical equation, the overall delta H for the reaction will be different from what it is for the other state of matter. This leads us to the next part of thermochemical equations, is that thermochemical equations can be treated like math equations. We can add and subtract them. For example, if you have an algebraic equation of 2x plus y equals 3, that equation can be added to x plus 3y equals 9 to give a total of 3x plus 4y equals 12. We can do the same thing with thermochemical equations. The addition of thermochemical equations from small parts to give one big whole equation is an example of Hess's Law. Hess's Law is useful because we can use Hess's Law to calculate delta H values instead of doing experiments. So we've learned 2 methods now for calculating delta H. One was doing calorimetry. That was in the previous video, where delta H of a reaction was equal to the heat energy change per mole. And our second way of calculating delta H is now Hess's Law. There'll be a third way that we'll talk about We can look at these two reactions and see if we can add them together and simplify them. If we look at the first equation, there are 2 moles of H2O gas in the products. The second equation has 1 mole of H2 gas in the reactants. If we want to add these two reactions together and simplify things, it might be useful to multiply this equation by 2 in terms of the coefficients. What would happen to the delta H then, if twice as much water vapor was condensing to liquid? Well, that would be times 2 also. If the two equations are then added together, this is the result. So that we've got 2H2 plus O2 plus 2H2O gas goes to 2H2O gas plus 2H2O liquid. We have to treat the delta H values the same way. We add those together after multiplying the negative 44 kilojoules by 2, and that works out to be negative 572 kilojoules for that reaction. Now this reaction can be simplified a little bit. Looking at the reactants and products, it's possible to see that H2O gas is the same in the reactants and the products. This is a lot like having X on both sides of an algebraic equation. Since the H2O gas really isn't changing, we can cross those out. It's the same on both sides of the reaction arrow. We can then write the overall equation of 2H2 gas plus O2 gas goes to H2O liquid. That releases more energy than just having the reaction produce H2O gas, which was negative 484 kilojoules. So this is an example of Hess's Law, where adding two reactions together can give you an overall equation and a new value of delta H. Here's another example of Hess's Law. In order to determine delta H for this first equation, we can use the delta H values and the given equations that are down below. Let's walk through this and just see how using Hess's Law can help. In this particular reaction, our target equation, the top one, is CH4 gas plus 3/2 O2 gas goes to CO and H2O. This is a reaction that a chemist can't really do. It's really difficult to have a carbon-containing substance react to form only CO2 and not have any CO2 form. But if one wants to know the delta H for the reaction, one would need to use something like Hess's Law, since we can't do that reaction in a calorimeter. Let's look at the two given equations then. The first given equation has CH4 as a reactant, and it's got 1 mole of it as a reactant. We probably need to leave that equation alone. The second equation has CO as a reactant, but our target equation has CO as a product, so this reaction needs to be reversed. I'm going to write the reversed reaction just below the first target equation. So there's the second target equation written in reverse order from what used to be the products to what used to be the reactants. If a reaction is switched in its direction, the delta H needs to get changed in terms of its sign. So instead of that reaction releasing energy as it was written originally, the reaction written in reverse is now absorbing energy. Let's see if the two reactions could be simplified at all. In terms of the two equations, we can see that CO2 gas is present in both the reactants of one reaction and the products of the other reaction. Since it's both 1 mole on each side, those are going to cancel each other out. We can also see that some O2 is in the products and some O2 is in the reactants. We could subtract 1/2 O2 from the products and 1/2 O2 from the reactants, and we'll see where that gets us. I'll write the new equation with the CO2 and the 1/2 O2 canceled out. So there's the new reaction with the CO2 canceled out. There's still 2 O2s and the minus 1/2 O2 that I took away from the product side to reduce that to 0. We can combine these two terms for the O2, and that would leave 3/2 O2. Now this chemical equation looks just like the target equation, where CH4 combines with 3/2 O2 to make 2 H2O liquid and 1 CO gas. We have to treat the delta H values the same, so those can be added together to give negative 607 kilojoules of energy for the delta H for this target equation, the same as this one up at top. That's an example of how Hess's Law can be used to calculate delta H for a reaction that a chemist can't actually do. Here's a picture of what Hess's law can do for us. Here's enthalpy, or delta H, on the y-axis, and here's some reactants and products. The reactants start out as A plus 2B. Those reactants could make an intermediate called C, and then C could turn into 2 molecules of D. Maybe a chemist is able to measure delta H1, or the change in enthalpy for the first step. And maybe a chemist could measure the delta H for step 2. But maybe measuring delta H for step 3 is not possible. However, with Hess's law, the step delta H3 can be calculated simply by combining delta H1 and delta H2. Here's an example, or a picture, of the reaction we just completed in terms of Hess's law with methane and O2. The delta H was known for methane combining with oxygen to make CO2 gas and water. That one was known. The CO plus oxygen to make carbon dioxide. That reaction was known in terms of its delta H. And so these two values, the negative 890 and the 283, could be combined to give the negative 607 kilojoules for the reaction of CH4 directly to CO. Now, the worst thing that can happen with a Hess's law problem is that you have more complicated things to do. Maybe you have to reverse a reaction and multiply by a coefficient. Maybe you have 3 equations to add up together and not just 2. But that's really it for Hess's law. They're kind of like puzzles. Some students really love them. If you like Sudoku or crossword puzzles, Hess's law might be the thing for you. This is the end of the Hess's law video. I hope you've enjoyed it. If you have any feedback, let me know.